It's on the video.
I didn't talk about these complex ions with the water. I just don't find it important enough. I'm not going to put anything about that on the quiz. And you don't have a test on this chapter, so we'll just...
Yeah.
No. Never seen it. Now you know from before how to calculate pH. It's -1 times the log of the hydrogen concentration. Haven't done that in a while.
What?
We did acids and bases earlier in chapter 4 in this class, but we never did any pH.
I don't remember this.
Oh, come on.
I'm serious.
Yeah, we had this table up in, what's his face? Like, JB? I don't know.
Yeah, JB?
Yeah.
Where'd you have?
Robles.
Robles, you did pH.
Roby's my
I don't
girl.
remember this at all.
No?
I'm serious.
No, we did this.
I don't know what you
Kyle.
did. I seriously don't.
Okay, so anyway, negative log of the hydrogen concentration is how we find the pH. For neutral water, when the Ka value is hydrogen times hydroxide, both those are equal to each other, so each of them are 10 to the -7. So that means that the negative log of 10 to the -7 is 7. 7 is the neutral pH.
There's a POH as well.
Neutral is 7. The higher the concentration of hydrogen, the smaller the power on 10, because we're dealing with 10 to a negative number for almost all of our hydrogen concentrations in all of these acids. So that's where that negative sign out there comes from, because the log of 10 to a negative power gives you a negative number, so we make it positive with that negative sign. Now, some of you did and some of you didn't learn that pOH is also something you can calculate. pOH is where you take -1 times the log of the hydroxide concentration. Now, those two are related to each other like this. pH plus pOH equals 14 for any solution. And if you need the pOH, you can just take 14 minus the pH of a solution, and that'll give you the pOH. Sometimes that's handy.
So wait, if it's just water, there's a POH of 7 and then a pH of 7 as well.
Yeah, they're both 7. Yep. And they always add up to 14. If you're writing this down, I want you to just take a moment. Spencer, go back 2 slides. Thank you. This equilibrium right here, this is always happening. Water is always breaking up into hydrogen and hydroxide in an equilibrium. If I add acid to water, what does that do to this equilibrium? Yes, I'm adding an acid, so that means I'm adding more hydrogen ions. It causes this equilibrium to shift that way. So what happens to the hydroxide concentration? It goes down. Does it ever go to 0?
No.
No, it can get really, really small, but it doesn't ever go to 0. So the hydrogen times the hydroxide is always this number. You with me?
Mm-hmm.
So if that number goes up, that number goes down. But they're always going to multiply to get that. And the same thing is true if you add a base to water. A base is adding hydroxide, which also causes it to shift to the left. So that number goes down.
So is that why they tell you to add acid into water? Not
No,
water acid?
the reason that they do that is because acids like nitric and sulfuric are real, they're dense. And so they will sink into water. It's very exothermic when an acid dissolves, very exothermic. It can get past the boiling point of water. So you can't even touch, if I add like battery acid to a sample of water, after a few minutes I can't even touch the side of the container because it gets so hot. If you add water to the acid, that's going to get hot on the top of the, if the water doesn't sink into the acid, it starts to boil on top of the acid, it can shoot right out. Dang. Which is pretty dangerous. That's why they tell you to do that. Now, if you have fairly dilute acids, it doesn't matter what direction you go. But for concentrated acids, you always add the acid into the water, so it goes underneath. Yep.
What's like the highest?
One time when I was in college, didn't realize how much energy was given off. I had a milk jug. I needed to get some sulfuric acid, dilute sulfuric acid. So I put into a milk jug water, and then I added the sulfuric acid to it. And luckily, I didn't pick it up and try to walk away with it. I was just letting it sit there. I was doing something else. And it melted the jug, and I had sulfuric acid going all over the place. Never forget that one.
Mr. Moore, come on.
Wait, so like for this year, what's gonna be like the highest concentration of anything that you work with, like an acid or a base that you work with?
After the AP exam, you're going to do a lab project, and you'll have concentrated nitric acid, 14 molars nitric acid.
Whoa.
Yeah, you'll use 12 molar hydrochloric acid. But the HNO3 is more nasty than the HCl. So
Seriously?
it's very dangerous, yeah. You're going to have it in dropper bottles. You're just adding drops of it at a time. But yeah, you see some pretty violent reactions. Not on a big scale. It's not like going to blow up in your face.
Darn it.
Dang!
I know. I'm really disappointed about
I always wanted things to blow up in my face.
that. Let's go forward 2 more slides. Thank you. All right. So, when we're dealing with a strong acid, notice my arrow here. It's not an equilibrium arrow, it's just a one single direction arrow. Because it's a strong acid, right? At the end, there is none of HA. Now the Zumdals have given us a hint. Is there really none of this that's there at the end? Do maybe even a few molecules stay together? Yeah, maybe a few. But you can go ahead and assume that all of it is gone. Okay? Now, for some people, they just can't handle when I generalize things, even if it's not necessarily true. If you can't handle it, that probably means you're a miserable person.
What?
Thank you.
You can handle it just fine.
You can do it. Michelle? Now, is it appropriate to use an ice table for when you have a reaction that goes to completion?
No.
Initial, change, and E stands for equilibrium. But when we don't really have an equilibrium at the end, how about E stands for end at the end?
Whoa.
Spencer, let's go down a little farther.
Should you assume the end is
Keep
0?
going. Stop. Oh. Yep, that's good. Now, let's say that we have 0.1 molarity of a strong acid, like HCl. At the beginning, you have none of these. Is that really true, though? What about this? At the beginning, you have 0 hydrogen ion concentration?
No.
Ah, you have a tiny little bit. Does that amount matter? No. You're going to change it by a lot, and so that little minuscule amount of hydrogen at the beginning means nothing. All right. So if this is 0.1 at the beginning, we assume these are both 0. We know for sure there's none of that. There's no A in water. If it's a strong acid, it goes to completion. That means that whole 0.1 molarity goes to 0. So that goes down by 0.1. Those go up by 0.1. If we want to know the pH of this solution,
Take
whatever the concentration the acid was at the beginning, that's the concentration of hydrogen at the end. Yeah? Yeah. So, Spencer, go ahead and uncover the rest of it. That's our calculation. For strong acids only, the pH, which is the concentration of hydrogen at the end, but it's very easy just to find negative log of the initial acid concentration. So if I say, what's the pH of 0.055 molar HCl, when you hear, oh, HCl, I just take that 0.0555, take the negative log of it.
So if you're given like the pH at the beginning and they tell you to find the concentration of hydrogen ion, how do you do that?
Take the inverse log of it.
Oh yeah.
So let's say that you're given a pH of 5.5. That's equal to negative log of hydrogen concentration. So if you need the concentration of hydrogen and you know the pH, move that negative sign over. And how do you get rid of the log?
E.
You take the inverse of it, which means the log means 10 to what power equals that number. So you got to raise that number to the power on 10. So it's 10 to the negative 5.5 power equals the hydrogen concentration. This is the inverse log. And on your calculator, where you have the button that says log, look above it where you have to press shift to get it. It'll say 10 to the x power. That's what that means.
some more.
Yeah.
Why can't we use E? Do we have to?
E is for natural log.
I know, but like. Wait, let me
Oh
think.
my god.
Now, pH means power of hydrogen. 10 to what power? It's based on powers of 10.
Oh, okay, that's why.
It's all based on powers of 10.
I thought it was like based on some kind of like various number combination.
No, it's not. It's just 10 to what power equals this. It's just a shorter way of writing the kind of hydrogen concentration.
Well, I don't understand why they use 10 instead of E. It seems like everyone uses E instead of
Because
Yeah, well, they use 10 this time. In most other chemistry applications, we use E. You're right.
I like him because we count our fingers.
Fine.
Yes. You don't want to have E fingers.
Nice.
Okay.
Spencer, let's move on. Forget that. Sacrifice it.
His reaction.
You know, numbers would be much easier to memorize if we used a 12-point scale.
Stop.
But then we can give a count.
All right. Now we're going to have a case where we have a weak acid. How do you find the pH of a weak acid? Well, you have to set up a nice table for sure this time. Are you done with ice tables yet?
Yes.
Never. No. It's going to
These
feel like
are
never.
pretty easily.
Yeah, we have this one, and then 2 more chapters. 3 chapters more that we have to use ice tables.
Oh crap, we have 4 points today.
So if we want to find the pH of a weak acid, you have to know the initial concentration of it. You'd write out the chemical equation for it. Now I'm looking up the Ka value. Tarun, you got your book. Can I borrow your book?
Don't forget this time, Drew. That's all right.
Hey, someone actually brought their book this time.
I always have my book.
I always
Usually
have my
people like ask me.
In the end, or toward the end of your book, there are some pages with blue margins. You see that?
Yeah.
The blue margins is the appendix. And on page A22, you have the table of Ka values for lots of weak acids. It's about half of the page. HOCl is on there. That's how I got that Ka value. So when you're doing the Zumdahl problems, some of the problems will give you the Ka value of the acid right in the problem. That's nice. But sometimes they'll just say, for HOCl, what's the pH of this concentration? You have to go back to the appendix and look. But it's on page A22. Write that down. A22 is Ka value too. Think it through.
That book is beaten up.
Yeah, most of them are.
I thought these were new.
No, you're not.
They're out.
No, the solution guides are.
Oh yeah, the
So if the HOCl concentration is 0.1 at the beginning, that number right there is 0.1. What are these numbers?
0 and 0.
Both zeros. Yeah.
Wait, seriously?
Always assume the H plus to be 0. There will be a time in a few weeks where you can't assume the initial concentration to always be 0. We're going to find out when that is. It's when you're going to have some reactant that's very sensitive to a hydrogen or a hydroxide concentration. But that's later on. Spencer, let's uncover that ice table. All right, so let's take a look at this. The 0.1. Now this is a weak acid. It doesn't go to completion. So this is going to go down by some amount. We don't know how much. It goes down by, we're going to call it X. And when that does, these go up by X as well. What's nice about this chapter is all the coefficients are 1s all the time. All right. So if we wanted to find the pH, that means we need the hydrogen concentration. We need that number right there, the equilibrium hydrogen concentration. Yeah?
Yeah.
How do you like solving for X when you have this kind of a problem? You like it?
I don't like that.
Not really.
I still need
These ice table calculations, we can make them much nicer. If you remember from chapter 13, I keep alluding to this 5% rule. Let's talk about it. Makes your work a lot easier. The Ka of this thing is 3.5 times 10 to the negative 8. And that's equal to the equilibrium products over the reactants, which is x squared over,
X squared over 0.1 minus X.
yeah, 0.1 minus x. All right.
I said it's quadratic formula.
Yep, me too, but we're going to see if we can avoid it. And here's why we can avoid it. Because what can you say about the size of x?
Small.
How do you know?
Because the K value.
It's a tiny K value. Look at that K value. That means that the reaction heavily favors the left side, which means that when it shifts to the right, it shifts a tiny little bit and then it stops. Yeah?
Yeah.
How would you compare the size of x to 0.1?
Less than.
A lot smaller.
It's not just less than, it is a lot less than. It's tiny. So does 0.1 minus a tiny number really affect the 0.1?
No.
Not much. If we could assume that that x is neglected, would that make our work easier?
Yeah. So
A
much.
lot easier. You're going to see why in a moment. But if we neglect the x here, can we neglect the x here too?
No.
We can't, because these numbers started at 0. And whatever x is, it's infinitely more than 0. Yeah?
Yes.
But even if it's small, it doesn't change 0.1 very much.
Okay, so.
So, go ahead.
So if we remove that x, all we have to do is times by 0.1 and take the square root of it.
Yes. Which is so much nicer. So much nicer. All right. So then.